This is assignment 4.5 by Roddy Pettit. So first of all, with an introduction to quantitative data. What is quantitative data? So before we've had qualitative data, which is descriptive data, and quantitative then is numerical data, which could be, say, a female gymnast is jumping, seeing how high they can jump in a vertical jump test. And then the result that they get from that, say 42 centimeters, that would be considered quantitative data. And why do we use it? So we're able to compare results and data together. Say one person scored 42 centimeters on a quantitative data test, or on a vertical jump test rather, sorry. And then someone else scored 31. You're then able to compare those results, and you might be able to from there identify why that outcome happened, like why person A got 40 something centimeters, why person B got 30 something centimeters. We're also able to make predictions based on collected data. So if someone that was this height and this weight scored, say, 40 centimeters on a vertical jump test, then someone around the similar weight, similar height might score around the same sort of score, maybe like 2 or 3 centimeters off. And we're also able to find trends in health. So by that, what I mean is from someone's set of results, if they conducted multiple tests, found multiple results, we might be able to identify whether they lead a healthy lifestyle or not, depending on what kind of scores they got, if they're near the normative of their age, their height, and their weight, stuff like that. So with data organization, when you organize your data, of course, it makes it easier to read and understand because of how quick you're able to read it and compare it to other stuff. So again, vertical jump test, you can quickly read what someone got. You could say, okay, person A got 51 centimeters, person B got 27, person C got 32. Anything like that is really quick. You can just read someone's name or not their name, just like what they're labeled, if it's a test where personal information isn't being given out. Or you could look at different aspects of the person, such as their height and their weight, and then look at the results that they got. And there is many different ways you can organize quantitative data, such as range, rank order, simple frequency, and group frequency. So range is so you get the highest result, say from a vertical jump test again, being 50 centimeters. And then you got the lowest, say it could be 30 centimeters. And then the range in between that, what you'll do is you'll get the highest number, which being 50, and then you would minus the lowest number from it, which was 30, so then the range would be 20 centimeters. Rank order is, say your table's all jumbled up. It's not in order whatsoever, it's just person A got 27, person B got 34, person C got 42. You'll then put that all in order from person who jumped the highest at the top and person who jumped the lowest at the bottom. Simple frequency is used when the number of participants is greater than 20 and when the range of the results is equal to or less than 20. You use the simple frequency distribution with a table that has 2 columns. One of them is for the raw data scores, such as say you're doing basketball free throws, then the amount of missed shots you had, or each person in the group had, would be that raw data. Say you could have the numbers 1, 2, 3, 4 to 5, or 1 to 5. And then the other column is for the frequency scores. And the frequency column is the number of times that particular score was achieved. So if they made, say, 5 baskets, if only 2 people had that down, the frequency table or frequency column would have 2 in it, and then if say 7 people only made 1 shot, then 7 would be in the 1. Group frequency, on the other hand, is used when there's a greater or range greater than 21 and with more than 20 participants. This is essentially the same as simple frequency, apart from the raw data table. Instead of it being specific, such as 1 to 5, it will have a group of things such as like 1 to 10 being one little row, and then 11 to 20, and then 21 to 30, all of those being separate rows instead of it going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and etc. Here is an example of the range, which I was talking about earlier. This should make it more simple if you were confused by my explanation earlier. So as you see here, gymnast A scored 20 centimeters, B 34, C 16, D 46, E 39. And you can see that the difference between 16 and 46, which is the lowest and the highest score, is 30, therefore the range is 30 centimeters. So here we've got the rank order for a sit and reach test for gymnasts. So we can see gymnast A got 33, B 29, C 31, D 39, E 36 centimeters. And then underneath the table you can see rank order. I put it in rank order. It goes 29, 31, 33, 36, 39, obviously lowest to highest, lowest to biggest, smallest to biggest. And now moving on to how to present data. There are multiple ways to present data. These can be scatter graphs, line graphs, and column charts. Basically, you want to be presenting this data in graphs or charts. This way it's easy for someone who's reading. Say you've done a bit of research, for someone who's reading the results, they want to be able to understand quickly and be able to identify quickly what the results of each participant were. So you can have a scatter graph, which is where you plot in each individual point and then draw a line of best fit. A line graph is, again, you plot each individual score, but this time you connect them all. And a column chart is also known as a bar chart. So it's, say, what someone got 37 on a vertical jump test, someone got 38, someone got 42. Each score would have its individual kind of bar or column going up a graph and then kind of peaking at the point of their score. You can see here the scatter graph. And of course with each graph you want to label it correctly with a title. As you can see here, it's figure 1, correlation between upper arm girth and chest throw in centimeters. You will always want to have down or note down the value, or not really value, but unit of measure that is used on them. So in this case it's centimeters. And on the left axis you can see chest throw in centimeters, and that goes from 500 to 950, and then upper arm girth along the bottom, and that goes from 20 to 40 centimeters. And then here you can see all of the points plotted, and then a line of best fit. So this graph doesn't really show much correlation. Well, it shows a positive one, but not very positive. It's not very strong at all, because you see someone that's got like 27 centimeters of upper arm girth only getting close to 550, whereas someone with 22 centimeters of arm girth getting around 725. So there, it doesn't really fit the line of best fit, because that person who had an upper arm girth of 27 just didn't get anywhere really near the line of best fit. Here we've got a line graph, and again you can see that this is titled Figure 2, difference in body fat percentage of biceps and triceps. And then you got the bicep on the left axis, tricep on the bottom axis, and then you can also see the legend at the very bottom of the graph. Skin fold calipers millimeter biceps is the blue line, and skin fold calipers millimeter tricep is the red line. Here we've got a bar/column chart, and again it is titled participants' time for the static and flying sprint in seconds, and that's supposed to say flying, not flying. Sorry about that. Left axis, it's got time in seconds, and then bottom axis you've got participant number, and again the legend is there, static sprint in seconds, flying sprint in seconds. And you can see here a dramatic change in the flying sprint and the static sprint for participant 12. So that is very easy for you to read, but the only problem with this chart is because the values are so far apart with participant number 12, kind of mucks up everything else for all the other results, because you're not able to see how many milliseconds in that second, within that second. So it's like 7 seconds, maybe 7.25 seconds, something around there. But if their result wasn't that far apart from their flying sprint test, then you would also have markings in between them to show you or give you a better idea of what actual score they got or what actual time in seconds they got whilst running. So next up we've got standard deviation. What is standard deviation exactly? So the standard deviation is a measure that is used to quantify the amount of variation or dispersion of the set of data values. A low standard deviation indicates that, or tells us that the data points tend to be close to the mean. So if your mean was 35 for a vertical jump test, then what this would mean would be, say 36, 34, that would all be a very close standard deviation, close dispersion to the mean. But this also means that the exact opposite can happen. So you could have a really high amount of standard deviation, a really high amount of dispersion. So using the same example, if the mean for a vertical jump test was 35 and you had someone getting 22, someone getting 45, 51, something like that, then that would be very high standard deviation or high dispersion because it's not close to the mean whatsoever. So how exactly do we find the standard deviation? So first of all, you want to work out the mean, which is just an average of all the numbers which you find by adding up all the values, and then say you've got 10 values, then you divide the value that you get for adding up all of your individual values, divide that by 10. And then for each number, you subtract the mean and square the result. And then you work out the mean of those squared differences. So, and then take the square root of that, and that's it. You're done. You found the standard deviation. It does sound quite complicated, but once you get the hang of it, it is quite easy and quite a simple task to do. So when you add the standard deviation bars to a line graph, then what this does is it displays the standard deviation error amount for all values, like all of the plotted points, resulting in an x and y, which are the axes, resulting in the x and y axes error bars, and this will mean that they're the same size and won't vary with each value. Now we're on to histograms. So what is a histogram? A histogram basically represents an accurate is an accurate representation of the normal distribution curve or the distribution of numerical data. As you can see here on the right, the frequency and the hitting percentage of everything. This histogram here kind of shows the distribution of the data that you got. So frequency, so the furthest to the left bars, you can see they're relatively low, and then getting towards the middle, much higher. So the reason that the closest ones are low is because not a lot of people hit in that kind of range, whereas in the middle you see a lot higher or a lot more people getting that hitting percentage there, which is around or in between 0.3 and 0.4, so around 30 to 40% hitting percentage. Basically why we use histograms is because, like I mentioned before, they're a really clear and easy way of reading the distribution of data. So from here you can clearly see that not a lot of people got a 10% hitting rate or 0.1% or 0.1 hitting percentage, or a 0.6 to 0.7, 60% to 70% hitting percentage. How do histograms link in with the normal distribution curves? So you can kind of work out on this histogram that we've got pictured here, kind of like a bell shape, which if I go on to the next slide here, you can see that the histogram is in fact a bell shape, like you kind of saw in this picture here.